Good morning, folks. This is lecture number 18, which is posted on, let's see, March, March 14th. However, uh, you are not responsible for this material for test number 3, which will be in 2 days, namely March 16, during the tutorial time. The material on this lecture, in this lecture, will appear on the final exam. And obviously, whatever we're going to be doing after the midterm is going to be heavily dependent on this particular topic. So at this point, we're going to abandon the concept of single degree of freedom, uh, which we have been dealing with in the last 9 weeks, and move on to 2 degrees of freedom. Pretty much everything that we do is going to be involving 2 degrees of freedom, because anything beyond two is the strategy and the plan of attack is exactly the same at 2 degrees of freedom, except that things are messier. Instead of 2 by 2 matrices, you're going to be dealing with n by n matrices if you have n degrees of freedom. Okay, and obviously item number 2 will appear as we go along. Natural frequencies of a multi-degree of freedom system, 2 degree of freedom system, and the corresponding vibration modes are going to pop up as we move along. Now let's consider these two masses, and they are attached like that, and each one of them can move by the amount x1 and x2. Just the very fact that you have two masses doesn't necessarily mean it's a 2 degree of freedom system. The degrees of freedom means that the the minimum number of independent parameters that determine the position of the system as a whole. In this case, you can hold, for example, block one stationary, you can grab it, hold it, and then mass two can move by itself. That's 1 degree of freedom. Or you can hold mass 2 and mass 1 can move by itself. So there are two independent parameters determine the position of this mass. So for example, if you look at the diagram on the right, there is one mass, but still this is a 2 degree of freedom system, because the fact that you have one mass doesn't necessarily mean it's a single degree of freedom system. It's just that x1 and x2 in that diagram tell you exactly how many degrees of freedom you have, two of them. These are independent. Two. Or in a situation like that, where maybe there's a torsional stiffness here, torsional spring, so this is also 2 degrees of freedom, because the unique position of the mass is determined by how much it goes down and by how much it rotates about that axis. Okay, let's concentrate on this and draw the free body diagram of this structure. So uh, let's say that well, the situation is shown here, x1 and x2 to the right. So what happens is that when you look at mass 2 alone by itself, mass 2 alone by itself, the spring says, the spring K2 says, no, 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 you can't go. So it imposes an opposite force to the motion of uh, the mass 2. Now, because action equal to reaction and these springs do not have any mass, this force is exactly the opposite of the force that's applied on M1. Okay, and of course the spring K1 also says you can't go, so it puts a force which is K1x1. So the free body diagram of these things are drawn. Let us write down the sum of all the forces on mass 1 equal to mass times acceleration. We get this. And sum of all the forces on mass 2 equal to mass times acceleration. And we get this, okay? Everything to the right is positive. That's why, for example, this is positive, this is negative, and this one, when you write a equation of motion for M2, this is going to be negative. Now, you can clean this up, and you can take everything to one side, and it's going to look like that. Two differential equations, which give you position on the masses 1 and 2, namely x1 and x2. If we could solve this for x1 as a function of time and x2 as a function of time, we'll get the position of the masses and the entire system at any time. The only problem is that these are coupled. You cannot just solve the top equation by itself because x1, x2 appears also in the top equation, and obviously x1 appears in the bottom equation. These are coupled equations. Now, of course, to solve a differential equation, you need initial conditions. And in this case, you need 4 initial conditions. In other words, tell me where the mass m1 is and what its velocity is at time t equal to 0. Tell me where the mass m2 is and its velocity at time t equal to 0. You need 4 conditions to solve this differential equations. Okay. We're gonna write things in the form of a matrix. That's why I put x1 and x2, which are the solutions of the displacement of mass 1 and mass 2 in a vector like that. It's a lot easier to handle things in the vector form than individual scalars. Now notice also, at least Inman, when they use a letter, bold letter, it means that it's a vector. We try to do that. Sometimes it's inevitable. You can't do it. But anyway, Inman tries to, whenever it's a bold X, it means that vector X consisting of 2 components, and the 2 components are X1 and X2, not bold. Now, if you take this thing and differentiate it, obviously you're going to get derivative of the first component and derivative of the second component. And x double dot is going to be, the vector x double dot is going to be x1 double dot and x2 double dot. These are obvious. Okay. Now, let us define a matrix M, which goes like that. So it's a diagonal matrix, and it's symmetric. You can see that. And a stiffness matrix, which looks like that. A matrix which looks like that, because that equation, the two coupled equation, I want to write it for you in the efficient matrix form. Both this M and K are symmetric, obviously. Now, this was the equation that we had on the previous page, equation of motion for the two masses. If you clean this up, you can see that it's going to be a matrix, this M times vector of acceleration plus this matrix K, which is called the stiffness matrix, times the position, x1 and x2 equal to 0. This looks like our good old single degree of freedom system, mass times acceleration plus stiffness K times displacement equal to 0, except that things are now in a matrix form and in vector form. So people write it like that. M, mass matrix, x double dot, acceleration vector, plus kx, which is the spring force basically equal to 0. Now, written for your convenience here, once again, we need 4 initial conditions. In other words, give me position of x1 and x2, mass 1 and mass 2 at time 0, and give me the velocities of mass 1 and mass 2 at time t equal to 0. Essentially, we have these 4 pieces of information that we need, but if you put them in vector form, there is this vector, initial position vector, and initial velocity vector, which are to be supplied in order to be able for us to solve the equation. Now, let us let me assume that this vector x, the unknown vector x, is, which is a function of time, by the way, is a constant vector times this function. Now you might say, wait a minute, where did this come from? Well, first of all, j is square root of minus 1. Now, there is no reason why we should go to complex solutions. We could have said vector x equal to a constant vector times cosine of omega t, or vector x equal to constant vector times sine of omega t. I could get away not using complex numbers at all, just use it like that. Now, this is not coming out of nowhere. There is something called Euler's formula, e to the j omega t, or let's think about it like that. E to the j omega t is cos omega t plus j sine omega t. That's called Euler's formula, okay? So let's not get hung up on this. Either this, the top one, the bottom one, or the last one, the middle one or the last one. Okay, if I differentiate this, because u is a constant, essentially I differentiate e to the j omega t. That's why I get a, sorry, there's a mistake here. There is a mistake here. There is a j missing. So derivative of e to the j omega t is j omega e to the j omega t. I will fix this thing. Well, I can't fix it. So there's a j missing here. That's as simple as that. Okay. And if you differentiate this thing one more time, you get another j omega, but j times j squared is minus 1, so we get minus omega squared times the constant vector u times e to the j omega t. I have also written this thing down if I took the very last expression. If I say x of t equal to a constant vector sine omega t, when you differentiate this thing, derivative of a constant vector, of whom it's just a constant, derivative of sine of omega, omega t is omega cos omega t, and you differentiate it one more time, you differentiate this thing one more time, you get a minus, you get another omega, so omega squared, constant vector u, and sine omega t. There is no mistake here. There was a mistake up there where j is left out. Okay. Now, before we do the rest of the problem, in this part of the course, because we're dealing with 2 degrees of freedom, sometimes you have to invert the 2 by 2 matrix. And this is a very simple expression. This is a simple, basically, recipe for inverting the matrix. So it's going to be determinant, you know what it is? It's AD minus BC. And the inverse of this matrix is 1 over determinant. All you do is to swap these two. You see that? D goes up there, A goes down here, and these numbers turn to minus, okay? So mi minus minus, swap these. This is a very simple way of inverting a 2 by 2 matrix. Okay, let's move on. So for your convenience, I'm not using J. I wrote it like that. X equal to U bar sine omega t. Differentiate it. You get omega and cosine. And differentiate again, you get minus omega squared sine. Now, I take these guys and put it in this mother of all equations. I don't have a damping, but it looks like a mother of all equation for vector form, okay? So if you do that, notice that there's a sine of omega t, because there is no damping here. This doesn't come into the picture. These two come. The sine of omega t is a constant. You can, and u times sine of omega t is common between these two. Take it out. So you get minus m omega squared. See, if you take this thing and multiply it by m, you get minus omega squared times m plus k equal to 0. First of all, sine omega t, if this is 0 for any t, I can divide through by sine omega t and say that this must be 0. Okay? So for this to be true for any t, then what it requires is that the product of this matrix and that vector must be 0. Now, that looks familiar. Remember, in your linear algebra course, you had a situation where a matrix, specifically that matrix that I'm referring to, just remember, it was A minus lambda I times a vector equal to 0. Didn't we call lambda eigenvalue and the vector eigenvector? Well, this is almost like that. Okay, this is not A, this is not I, but it's almost like that. This is why it's called a generalized eigenvalue. This omega, the omega squared, plays the role of your eigenvalue, and u bar plays the role of your eigenvector. Okay? Later on, we're going to call U-bar a mode shake. But anyway, let's not worry about that. Essentially, this got to be 0. Now, how can the product of a matrix and a vector be 0? Well, one way, if U is 0, but if U is 0, that's totally useless because it says that X is 0. These blocks don't move at all, right? Because after all, if U is 0, the position of the two masses, x1 and x2, which are components of this vector, are 0, and that's totally useless. So this cannot be 0. How can a matrix times a vector which is not 0 be equal to 0? The only way that can happen is that if the determinant of this thing is 0. So the only way U can be a non-zero vector is that if this is 0. Okay? That's exactly the kind of thing that we did when you took your linear algebra class. You says determinant of A minus lambda I. Okay? But that was a standard eigenvalue problem. This is a generalized eigenvalue problem. Therefore, that's why I don't see an I here. I see an M. And the thing that was called lambda is omega squared. That's okay. That's all right. This omega is the natural frequency because after all, look at it. Look at it. If I'm saying x of t equal to a constant vector times sine omega t, that means these masses, m1 and m2, are moving at that frequency because it's a constant value, first component of u times sine omega t, second component of u times sine omega t. Basically, it says that masses m1 and m2 are oscillating at frequency omega. Okay, that's why these are called natural frequencies. Now, unfortunately, or I don't know, whenever we did single degree of freedom, when I wanted natural frequency, I called it omega n. We're not going to do that here because that's going to cause a confusion. So every time we say in this context omega, this is the natural frequency. I'm not going to write omega n squared. Okay. Now, once you find the natural frequency omega, then you go and find this vector u. And this vector u is called the mode for each uh, natural frequency. Okay, it plays the role of your eigenvector as you did your linear algebra class. Okay, let's remember that's the situation. This is the this is the equation that we have to solve to find omega first, find the natural frequency, and u, which is called the mode, later. Okay, written here for your convenience. So determinant of this must be 0. Well, let's write down. What is M? M was M1 and M2. Remember, matrix M was a diagonal matrix, M1, 0, 0, M2. Remember this matrix K was actually right here, K1 plus K2 minus K2 minus K2, K2. Literally write this thing down. Write M, write K. You're going to have determinant of this. You know how to find determinant of a 2 by 2 matrix. This product minus that product. There we are. This product minus that product. It's written for you. Notice that it's a fourth order uh, algebraic equation. Actually, to be fair, this is not really fourth order because if you call omega square something, this is the square of that. In other words, just hypothetically, if omega squared, I call it the alpha, this is alpha squared. Alpha squared minus alpha plus a constant equal to 0. But it's a fourth order algebraic equation, fourth degree equation. These are called characteristic equation. Whether you talk about this or that or that, they're saying the same thing, and these are called characteristic equations. Now, when you find omega squared, you can take plus or minus omega 1 and omega 2. See, when you get like, for example, omega squared equal to 25. Then omega 1 is plus 5, omega 2 is omega 1 is plus or minus 5, and if you find omega squared is 36, omega 2 is plus or minus 6. Okay, so as I said, this is really not a fourth degree equation. it is a second order equation, and that's really what this is saying. Now, so we found omega 1 and omega 2, and we have to multiply it by vector u1 and u1. Vector u1, this was the eigenvector. These are omegas that we found, plus and minus. And we do the same thing for omega 2. We found plus or minus omega 2. That's why one has plus, the other has minus, multiplied by u2. Actually, this is called Euler's equation. In other words, if you add these two up, one has a positive exponent, the other has a negative exponent. If you add these two up, you see that actually u1 is common. You get e to the j omega 1t plus e to the minus j omega 1t. There, you see that the sum of these two is going to be 2 times cosine of omega 1t. And if you add these two, again, you're going to get u2 times cosine of omega 2t. If you subtract them, you're going to get u1 times j times 2 times sine. All I'm trying to tell you is that, look, instead of taking it like that, you can, if you don't like complex numbers, you can look at it like this. Where are these coming from? Where did we get sine? We took these and added them up and subtracted them. And the two that you get when you add these two up, you can divide through. Okay, these are going to be solutions. So u1 sine omega 1t, u1 cosine omega 1t. This is the uh, eigenvector or the mode associated with omega 1. This u2, this is the same thing. These are the same thing. U2 is the eigenvector or the mode associated with omega 2. And we'll do example in a minute. So these are all solutions. So what is the total solution? It's a combination of these. A of this times B of that times C of that times D of that. Add them up. How do we find this A, B, C, and D? Remember, you need 4 conditions for initial conditions. Now, by the way, this is fine. There's nothing wrong with this. Each one of these multiplied by a constant added is going to be a total solution. But remember that whenever you have the product of things which involve the sine and cosine, uh, uh, this see, whenever we have sine cosine of the same frequency, or sine of the same frequency, or cosine of the same frequency, instead of writing it like this, it is possible to write it in this form. In other words, you can combine these. Okay, whenever you have sine and sine multiplied by these constants, you can combine them so that you have a phase angle and an amplitude. Okay, and I just want to remind you what this A1 is. A1 is square root of A squared plus B squared. Same thing with this one. This A2 is square root of C squared plus D squared. So this is a solution, but this can be massaged to look like that. This is also a solution, whichever is convenient. Let's do an example. So suppose we have a mass M19, mass M2 equal to 1. This stiffness is K1, and this stiffness is K2, 24, and 3. Let's write down the mass matrix. Well, here's what we have to do first of all. First of all, find the natural frequencies and the modes. And once you do that, do something, check something out. Don't worry about B right now. Our job is to do A right now. We come back to do B, and we come back to do C. Don't worry about it right now. Just A for now. So this was M, this was K. Plug in M1 and M2, plug in K1 and K2. You get this. So what is that matrix? Characteristic matrix minus omega squared M plus K. Now, let me remind you that if you thought that this was equal to 0, we're not saying it's equal to 0, but if you thought about this being equal to 0, they'll tell you that omega is the square root of k over m. Don't think about it like that, because square root of k over m, k is a matrix divided by m is a matrix. You can't do stuff like that. All I'm saying is that you have seen in the single degree of freedom, it was exactly the same thing equal to 0. And that's how we got k over m, root of k over m. Here we can't do that, but we have to write this and take the determinant of it, set it equal to 0. We are not saying this is 0, we're saying this is singular, because this thing multiplied by u gave us 0. Okay, doesn't mean this is 0, but the determinant of it must be 0. So let's literally write it down. You have your m, you have your k, just there it is. Just multiply it out. This minus that, you get this expression. Do the algebra, you get this, and divide by 9, you get that. Notice it's very easy to solve. Actually, it factors omega squared minus 4 times omega squared minus 2. If you multiply that, you get this, and obviously you get the one on the top. And you get your frequencies, plus or minus 2, plus or minus root 2. Now notice that we don't have to take both plus and minus. We can take only the pluses, because one of them will be multiplied by sine, the other one by cosine. Okay, so all right, let's move. So omega 1 is 2 rad per second. Omega 2 is root 2 rad per second. Okay, let's proceed. So we just did this. We got these values. Now we have to go and find the mode. Let's find the mode, or the eigenvector, think about it like that, associated with omega 2 equal to root 2. So we have to go and plug it in here. Remember, this times u1 equal to 0. Our job is to find u1. The first mode associated with, uh, this is a bad way of writing it. I would have liked to write this thing as u2. I would have liked to write this thing as u2, but unfortunately I didn't do that. Okay, so just plug it in. Okay, so this thing with that value of omega 2 equal to root 2, just plug it in. You're going to get that equation. Okay, I'm sorry about this. I would have liked to call this thing u2. Now, sure, let's if you look at these two equations, these are identical equations. The top equation is the bottom one multiplied by 3. That's minus 3, actually. That's all there is to it. So we really have only one equation, either the top one or the bottom one. And because we have only one equation, we have some freedom to choose u1 and u2. Because the equation that we have is minus 3u1 plus u2 equal to 0. So I arbitrarily set u2 equal to plus 1, and I'm going to get u1 equal to 1/3. So this, okay, is the first mode. And I'm really sorry about this thing. If I had called this thing omega 1 instead of omega 2, I would, this still would all make sense. There's nothing wrong with this thing, except that I don't know why I started with omega 2. If I had called this thing omega 1, this would have been, everything would have been fine. It's just that terrible. Okay, now let's go ahead and take the other frequency, omega 1 equal to 2, omega equal to 2, plug it in the corresponding equation, except that instead of root 2, you have 2. Just plug it in here, okay? Now, yeah, and the equation, if you write this thing, equation going to look that, where omega 1 is actually 2. Just literally plug it in. Once again, these two equations are identical. One is 3 times the other one. So really, I have freedom to choose one of these variables u1 and u2. So arbitrarily, I'm setting u2 equal to +1. And that'll give me u1 equal to -1/3. And I found the second mode. First mode, second mode. Okay? This goes with root 2. This goes with 2. Okay, just keep that in mind. Now, what do I mean by orthogonality? Notice that I found a u1 and u2. If you find the dot product, if you find the dot product of these two, you don't get 0. You get some number. But but if you do, if you put an m between them, in other words, u2 dotted with mu1, and this is one way of writing it, you do get 0. And the same thing, if you take u2 dotted with ku1, you get 0. So these two modes that I got, they are orthogonal to each other. The dot product is 0, almost, because the dot product is not 0. The dot product, if you put an m in the middle and a k in the middle, you get 0. So this is not the kind of orthogonality that you were taught in linear algebra class, but it holds for vibration. The modes are mass orthogonal and stiffness orthogonal in this sense. Okay. In general, this is not true though. Okay. Now, part C says, okay, what if I gave you 4 initial conditions? Can you write the solution? Well, we found the 2 frequencies and we found the 2 modes. So these are the initial condition, initial displacement, and initial velocity is given to you. This was the form of the solution one way, or I could have combined these two, so that A1 and A2 and phi 1 and phi 2 are unknown instead of A, B, C, and D. So I'm going to use this. First of all, you know, you know the initial condition. For example, t equal to 0. If you set t equal to 0 in this expression, you know that this vector should be 1 and 0. Okay? Uh, let's write down what we know. We found u1 and we found u2, the modes we found. This one went with root 2. This one went with 2. I just want to double check on that. Please, can you? I'm going to back up for a second. 1/3 and 1 went with root 2. I'm sorry, I have to back up. 1/3 and 1 went with root 2, right there. And minus 1/3 and 1 went with 2. So let's go back here. And I'm really sorry about this. Yeah. 1/3 and 1 went with root 2, minus 1/3 and 1 went with 2. Okay, so uh, now we set t equal to 0. Well, we need to take the derivative of this also because there is a condition that we need on the initial condition on derivative. So I take this thing and I differentiate it, or I take this after I plug in your values u1 and u2 as vectors and differentiate it, I get this. Now I'm going to set t equal to 0 and set this thing equal to 1 and 0, and t equal to 0 in here, set it equal to 0 and 0. I get, for your convenience, written again. Okay, this is the derivative. At t equal to 0, this whole shebang, when t is 0, which reduces to this, is 1 and 0, right there. And this whole shebang, when t is 0, is 0 and 0, which is this. 4 equation, 4 unknowns. By hooks or by crooks, you have to solve it. This is one equation. These are 2 equations. These are the other 2 equations. This one is that top one. These 2 is that bottom one. Somehow you have to solve, somehow, and you're going to get this. So now that you have A1 and A2, you have the number A1 here, you have the number A2 there, you have phi 1 and you have phi 2, and you can plug these things in and you get your uh, yeah, you get your solution right there. Now notice that we have something plus pi over 2, so we wrote it. Inman decided to write these things, get rid of the phase, and write it in terms of sine becomes cosine, this sine becomes cosine, etc. So, and we have plotted it. So the red one is the motion of the mass 1 as a function of time, and the blue one is the motion of mass 2 as a function of time. You have to use matrices. If it's a 2 degree of freedom system, these are going to be 2 by 2 matrices. If it's 3 degrees of freedom system, it's going to be 3 by 3 matrices. And of course, n degrees of freedom, n by n matrices. Now you can see why I did not want to call omega n, because there will be a confusion between, is it the number of degrees of freedom that this guy is talking about, or is it natural frequency that the guy is talking about? Omega n, use of omega n is a bad idea for these problems. Okay, so the one thing you want to notice is that if you look at the solution to this problem, both frequencies will participate. So the motion of mass 1 involved both frequencies. Motion of mass 2 involved both frequencies. However, if your initial condition, remember those 4 conditions, x dot at 0 and x of 0, if x of 0, that initial condition is one of the modes, u1 for example, u1, which was 1/3 and 1, something like that, and initial velocity is 0, believe me, you calculate this, both of these will only involve that one frequency, which was with that mode that I was talking about. So here, if the initial condition, as far as displacement, is this mode, which corresponds to root 2, and the initial velocity is 0, then if you repeated this, you get x1 equal to something times sine of root 2t, and x2 equal to root 2 again sine of, sorry, not root 2, sine of root 2t. Okay, so if these are select initial positions are the modes of the vibration, first mode, then both mass will vibrate at a single frequency coming from that mode. If you took the initial condition to be this went with 2 rad per second, both masses will vibrate only with that frequency. Otherwise, both omega 1 and omega 2 are going to be present in your solution. Now, this is going to be one of your homework problems. When you think about it, this is exactly that problem, the problem that we did today, except that there were no dampers. There were no dampers. Okay, and there was nothing on this side. So K3 is 0. If K3 is 0, there's no spring here basically, and there are no dampers. This is exactly that problem that we did just a minute ago. All right, and you have to do that as a homework. You'll do that. Now, remember, I showed you as a block because blocks are easy to think. Translational blocks are easy to think. But here is a situation where you have 2 disks. These are rotational motion. These are torsional springs. Okay, and the degrees of freedom. It's a 2 degree of freedom system. Degrees of freedom are the angular positions. Some information is given. First of all, it says write the equation of motion. And once you wrote the equation of motion, suppose that these two are the same stiffness. For example, the same material, same length, same diameter, etc. And assume that the mass, the mass moment of inertia, polar moment of inertia of this is 3 times that. So work out the natural frequencies and the modes and things like this. So the equation of motion, again, draw the free body diagram. Okay, so let's assume for the sake of argument theta 1 is bigger than theta 2. So if you look at this thing, this trying to rotate, that spring says no, 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 opposite. And if this spring also says no, 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 no. Springs always resist motion. Springs always are opposite to the direction of motion. Okay, and of course for this one it's going to be, because we are assuming that these are massless. Okay, so on this disk it's going to be exactly the same number except in opposite direction. And write down the sum of all the moments about this axis equal for block 1 or for disk 1 is J1 theta 1 double dot. These are moments. This must be J theta double dot. Okay, and write the same thing for this fellow. You get that? We're going to clean this up by introducing a vector, rotation vector, which is theta 1 and theta 2. This is our rotation vector, the counterpart of the x vector, which has two components. And you clean it up, you get the mass matrix, symmetric mass matrix. Now, these are, of course, because of rotational motion, they're polar moment of inertias, okay? And this one is same thing that we had before, equal to 0. This is the mass matrix. This is the stiffness matrix. Both are symmetric, as you can see. Now, for the particular value that's given, it says J1 is 3J2. I've written it here, right there. So this is 3J2 and this is J2, right there. Of course, J2 is going to go with us because it's a number that we are not told what it is. And this is a value, it's a constant, but you just have to carry it, that's all. And you're told that K1 and K2 are the same, so this K1 plus K2 becomes 2K. So the K can come out. So there is your mass matrix, equivalent mass matrix. So there is your equivalent stiffness matrix. I say equivalent because this is a torsional spring. Now you follow the rule, determinant of minus omega squared m plus k equal to 0, but it's not m, it's j. Okay, so just literally write it down. Write down matrix J, this is matrix J. Write down matrix K, this is matrix K. You're going to get something like that. Determinant is easy, the product of these two minus the product of those two, and solve it. You can solve it. Those are quadratic equations. You can solve it, and you're going to get this. These are the natural frequencies of vibration of those two, uh, of that 2 degree of freedom system. Now, let's go ahead and find the first mode shape. So remember, you have to take the first frequency, put it in the expression of minus m, or minus omega squared times m plus k times u equal to 0. And if you do that, you see that actually these are not two equations. These are the same equation. Therefore, we have freedom to decide to give one of these, choose one of these. So for example, I can choose U1, 2, this one to be 1, and find U2, U1, 1 in terms of that. Now, for the second mode shape, take the other frequency. Remember, there are two frequencies with those weird numbers in front of them. There was 2.33, and then I think it was 1.434, something like that, in front of them. Just literally put the second one in there. Again, these are two equations, but they're identical equations. One is a multiple of the other one. So it's really one equation which looks like that. You have a freedom to choose, for example, the second component, and you're going to get the first component out of it. So these are the modes, vibration modes, torsional vibration modes, which means eigenvectors of that particular problem. Now, this is a different problem. Notice that there is no spring to the left of this J1. So it's essentially two disks attached with a spring in the middle. So this is almost the same problem, except that there is no spring to the left of this attached to the wall. Okay, no problem. Now, we can go to the previous problem and set this, the stiffness of this spring to the left equal to 0. So I can salvage whatever I have done by setting K1 equal to 0 and K2, this is K2 equal to, okay, no problem. So if you do that, this doesn't change, J doesn't change, it's the same J matrix. This one does because K1 is 0, so there's no such a thing here. It looks like that. And K2 is K, okay, fine. There is going to be your equation, determinant of omega squared times the mass matrix, equivalent mass matrix, plus the stiffness matrix equal to 0. And you're going to get, you just look at this, when you solve it, you're going to get omega 1 equal to 0 and omega 2 equal to 1.155, instead the square root of K over J2. Now, when you think about this thing, this makes sense because this can rotate as a rigid body. In addition to vibration with that frequency, it can also rotate as a rigid body without any essentially oscillation. And that's what this thing is telling you. So there is rigid body motion. When there's a rigid body motion involved, there's always a zero frequency. And the other one is, of course, is the oscillation frequency. In other words, let's hypothetically say I took this thing, grabbed the left disc, rotated the right disc, and let it go. Both will start to oscillate, and it's going to be at that frequency. Essentially, this essentially can be viewed as a it's not a single degree of freedom system, but anyway, one of the frequencies is 0. Let's find the first mode. Okay, so we take that first mode, omega equal to 0, plug it in there. What do I mean by plug it in there? To find the mode, you go and put it in the equation minus omega squared times a, m, plus k times u equal to 0. That's what I've done. Okay, except that because omega is 0 first mode, omega m squared is not going to come into the picture. It's just ku equal to 0. And of course, you're going to get, these are the same equation. You're going to get rigid body mode, rotation of the same amount of the two disks, 1 and 1, or 2 and 2, or minus 3 and minus 3. Okay. For the other one, just literally go ahead and plug in that other value of omega and write it down. Okay. You're going to get 1 and minus 3. Okay. So let's look at another problem that we want to do. We have another 4 or 5 slides. Let me just take a quick break here. Okay, quick break means a sip of water. So this looks familiar to you, right? When you take a car, the simplest model of a car is take the mass of the entire car going up and down. So it's a single degree of freedom system. And then, suspension system, the stiffness, shocks, etc. It's a single degree of freedom system. We have done problems like this. But it is also possible to view this thing as having 2 degrees of freedom. Bounce up and down, which is exactly this, but the pitch, okay? This thing can pitch about the CG as a straight line. So essentially, we have this situation. So there's a CG of the car. It can go up and down. But this car, if we viewed it as the chassis as this straight line, it can actually rotate. So this has 2 degrees of freedom, angle theta and motion of the CG up and down. Okay. Now, if you think about it, when uh, this thing comes down, the CG comes down, and this thing rotates in the clockwise direction, uh, the amount of stretching, the amount of this displacement, actually, you can see that displacement is going to be x minus L1t, because L1t Remember, this is coming down and this is going up. So one is positive, the other one is negative when you look at this coordinate system, okay? So this is x minus L1t, and on the other hand, this one is x plus L2t. You can see that this is coming down by the amount x, but this rod is also rotating, and this amount is L2, that length, times this angle theta. So when you look at this, you can write sum of all the forces in the vertical direction equal to mass times acceleration of the car, and sum of all the moments about the CG equal to the inertia of the car, polar moment of inertia of the car, J of the car, times the theta double dot. We have done things like that, except that uh, this is a 2 degree of freedom system. So we're assuming that there are small angle oscillations, therefore that length is L2 theta and this length is L1 theta, etc. So, as I said, sum of all the forces in the vertical direction, in the x direction, equal to mass times acceleration, mass of the car times acceleration. Sum of all the moments coming from different forces that are have these sources equal to sum of all the moments equal to J of the car about the CG times theta double dot. Okay, so here's the situation. This is the same diagram, repeated for your convenience. Sum of all the forces, what are the forces that are acting? Okay, there is the damping force, vertical damping force. It's derivative of this times C1 right there. And there's a spring force, okay, which is right here. Spring force always resists the motion. Damping force always resists the motion. So this is the spring force, the spring on the left. This is the damping force, the damper on the left. And we also have the same thing on the right side, okay? They're both negative, as you can see. This is negative, C2 is negative, the coefficient of C2 is negative. But the amount of the velocity on the right is the derivative of this, which is right here. Derivative of this thing is right there. And the amount of compression on the right side is x plus L2t. So resist the motion of the spar trying to go down. And you do the same thing, same forces, but moment about CG. And please go ahead and do it yourself, because it is just for example, if you look at this hypothetically, the moment of the stamping force, you have to multiply it by the moment arm, which is L1, right? L1, right there. This is the moment arm of the damping force here. For the spring force right there, again L1. For this damping force, the moment arm is L2. And for that spring force, the moment arm is L2. So patiently write the moments of these forces about the CG, which means you're going to have these moment arms, equal to J theta double dot. J is, if you look at the car, it's represented with this line, okay? And obviously there is a mass distribution along it, so we're assuming that somehow the the the, the mass moment of inertia of uh, the polar moment of inertia of the mass distribution of the car is given by a single number, which is called J. Well, let's assume that since it may be easier for somebody to give us the radius of gyration of the car chassis. The relationship between radius of gyration and the polar moment of inertia of the car is just mass of the car times that radius. So if somebody gave us R somehow, they said the radius of gyration of the vehicle is R, I just take the mass of it, multiply it by R squared, and use it as J. So there we are. If you get rid of J instead of writing it as mr squared, this is the equivalent mass matrix. This is the equivalent damping matrix, and this is the equivalent stiffness matrix. Somehow we have to solve this equation. This is the equation of motion, and we have 3 weeks to do it, and we will. So essentially, if we ignore damping because we haven't really decided on what to do with damping, if we ignore damping, this matrix go away, and this is not any different from the previous two problems that we did. Okay, there's a mass matrix, there's a stiffness matrix, x equal to 0. So we have, as I said, the next 3 weeks is precisely solving things of this type. But I want to digress a little bit and ask you a question. Go back to your first year calculus class. Somebody gave you these two, an integral like that and an integral like that. And it said, he or she said, your instructor said, which one do you like better to calculate? If you had a choice of doing this or that, which one would you say? You look at this and say, oh my God, this is a disaster. Well, I'm going to go with this. I know the integral of e to the x is e to the x, and then plug in the upper and lower limit. But most people will pick the top one. But these, if you make a change of variable, you see, this is what scared you. X squared minus x scared you. If you call it q, this thing, 2x minus 1 dx, is just the derivative of that q. In other words, if you call this thing q, dq dx is 2x minus 1. So these two actually are the same. This thing is exactly e to the q dq. Of course, the limits are good. So isn't that the same? But it's the nature of human beings. This scares me. Let me do this. But it's simple change of variable will actually give you the same integral. Same thing, just look, it's just the limits are different. Now I have another question along the same line. Go put yourself in the differential equations course a year later. Somebody gives you this, and somebody gives you that. So which one do you prefer? You're going to say, okay, let me write these things down, see what they say. If you look at this, just literally multiply this thing by that, multiply this thing by that, equal to 0. Multiply this by the second row, this by the second row equal to 0. So it looks like that. Repeat it for down here. You look at this, you say, wait a minute, there's no x2 here. And you look at this, you say, ooh, there's no x1 here. So obviously, I'm not going to do this because this has x1 and x2 in the same line. But this one has no x2 and this one has no x1. So these are uncoupled. These are coupled. I can solve these. I mean, the first 3 weeks of the course, the first 6 weeks of the course, basically has been stuff like that. As a matter of fact, when the right-hand side is 0, we have solved this thing so many times. But this one, they're coupled. You have a problem. So the question is, can I change a variable just like I did in the previous problem so that these two equations becomes uncoupled? And the answer is yes. And the trick is this change of variable, instead of x, use another vector q. This matrix is going to be a 2 by 2 matrix, and in it you have your modes, eigenvectors, modes, and you have what is that? Almost 4 weeks, 3.5 weeks to discuss these things. Don't be scared, but be prepared. Okay, so this stuff is not going to be on test 3 in 2 days' time, March 16th, but this stuff will be on the final exam, and everything that we do in the next 3 weeks, it really goes down to matrices, natural frequencies, and eigenmodes. All right, folks, so good luck on your test. Please make sure you watch this before you come to class after the midterm, after test number